Hi, I'm Ashutosh Jagni. Um, I'm here to present my work on extending cell tower coverage through drones. This work has been done along with my colleague Mahant Gowda and our advisor Professor Romit Rai Chaudhary. We have all experienced a lot of network outages or loss in data while we are walking in places like Manhattan or places somewhere in Chicago where there are large towering structures of buildings. We do rely these days on having our cell phone operators give us really good data. But what happens in these places is, uh, is really not that pleasant. And we have seen a lot of reports like this in the news. Just to test out what really is going on here, we actually conducted similar experiments at our campus at UIUC. And what we found is dead zones or lowering of data throughput at places near large buildings is not unique to only Chicago or Manhattan. It is actually happening everywhere, even at the University of Illinois, where the buildings are not that large. We do see more than 20 dB of difference between SNR somewhere close to a building and somewhere in the open. What this points to is potentially two problems. One being RF shadows, that is shadowing caused by the building structures themselves, and the second being congestion created because there are just too many users at a particular place. Of course, the network operators are aware that these problems exist, and they try to solve it in one of two ways. First is to drive in a cell on wheels solution. If suppose you are going to a cricket, going to a football match or a concert, you might actually see these kind of towering structures. These are nothing but cars with cell towers on top of them. They allow coverage for a stadium or for a small gathering of people. However, this kind of structure needs some planning. It cannot be deployed in like 5 minutes. It needs pre-planning and information for the cell phone operators to actually cater to such crowds. Another way in which cell operators do cater to these problems is by tuning their antennas, the directionality of the antennas, and the gains in a particular direction. Now, this helps to increase coverage in areas where shadows are caused, but can never eliminate shadows completely, because no matter how you orient your antennas, there will always be some region which you cannot cater to. There is a third solution, which I am not pointing out here, which is essentially to over provision. Just go out and place too many antennas all over. That has two issues. One, too much of radiation, and second, the real estate costs of just putting out antennas everywhere you can find it just getting out of hand. So what are we proposing? Something something slightly new. We are trying to fly in drones which can support small flash crowds as well as be able to deploy anywhere easily whenever we need it. This can respond quickly to changing demands and can move in an interesting location whenever we need it. So now we can cater to hotspots created by flash crowds because someone was really playing a good guitar and not just because there was a big music console. Of course, to make something of this sort feasible, there are a lot of pieces of this puzzle. We will be concentrating on an important piece of puzzle, but will not be solving the entire solution space. We are concentrating only on placement of the drone. If we are to fly out a drone to cater to a certain demand, how is it that we will be able to place the drone in the right position? And it turns out it is actually interesting because if there was a single client, you could just take the drone and make it fly on top of this person's head and create a cone of coverage just for this one person. This will connect via wireless backhaul to the original cell tower and cater to a shadow that would have been created by this building. But the problem quickly becomes more interesting when we have a few more people. Now what we want is for the drone to cover all of these, and therefore it can no longer just stay where it was, but it has to go probably higher to cover a larger area so that more people are covered now. What we are essentially getting into is that placing the drone at a location which will cater to all the required clients is not simple, and there can be various solutions to this. As a third example, let us assume that two clients are located as shown here. Then the solution for this is for the drone to hover somewhere laterally, very different from the previous one, and now provide coverage to both of these clients. Essentially, what we are talking about is if we could have created an entire three-dimensional SNR map of what will happen if a drone is positioned at various places in this 3D space, then we could have solved this problem. We could have given a particular placement of clients, we could have constructed an entire three-dimensional SNR space and placed the drone exactly where we want it to be. However, this is going to be very challenging because that will require the drone to traverse the entire three-dimensional space, which is very much expensive. So let us quickly talk about the challenges. We cannot keep going higher and cover everybody. It is like the moon sees all the clients, so could we place the drone on the moon, for example? We can't do that because even if it increases coverage, we actually lose a lot of energy which is dissipating on top of the buildings and going away. We cannot also do that because even though most shadows can be avoided, we are increasing the path loss due to distance to a very great degree. We cannot come too close to the clients, not just because the clients will be afraid that the drone will fall on them, but also because it increases the amount of physical obstruction avoidance that the drone needs to do, and also because the drone itself will now start entering the shadow regions. Moreover, a possible solution, which was mapping the entire 3D space, is really not feasible because the drone will just end up wasting too much of battery and not really provide any beneficial solution at all. Also understand that the physical space of what the drone can be covering can be really large. It could be multiple blocks of buildings. So this can become very expensive. As a result, this is the problem that what we are looking at in this paper, strategically placing a drone such that it can provide good coverage to multiple clients. An opportunity exists because positions of buildings are well known. At least for a few months, hopefully, buildings remain stationary where they were originally placed. Also, radio propagation, or the way in which radio waves will work or propagate, is known. And therefore, recomputing of 3D SNR space should be possible even without flying the drone itself. And for this, we use a technique known as ray tracing. Ray tracing is very well known in both the Wi-Fi space as well as in graphics. What happens in ray tracing is we have an object which is termed as a transmitter, and we want to see what is the impact of radio waves transmitted from this place on other places, such as one explained here as the RX, as the receiver. So we want to basically map the SNR space for this entire three-dimensional area, but we are giving an example of just having one RX. The ray tracing technique tries to emit rays from the transmitter, and various obstructions which are known and therefore modeled in the system reflect those rays and cause diffractions and reflections and absorptions, and all of those are calculated, finally giving us the SNR at the desired location. Now this technique can be made arbitrarily complex. We will talk about that in a bit. But what we are trying to do here is, given known locations of the clients, we try to estimate the signal strength at each potential drone location. And once we do that, we can give an estimate of where the drone should go and hover. Now to validate whether this works well, we actually made some drone flights at the engineering quad at UIUC. And this is an interesting area because it is open so that we could actually fly the drone. And it also has a few buildings around which can be modeled into the system. And we can see how reflections across these buildings will affect the SNR at each client. By the way, we used a X8 drone and a Wi-Fi access point because we did not have access to a mini cell tower relay. So we used a Wi-Fi access point. to do these experiments. And we placed Raspberry Pi clients around in these locations, somewhat hidden and somewhat in the open. We modeled these buildings using Google SketchUp, and then a ray tracing system called Wireless Insight was used to produce the ray tracing results. So what we saw is that ray tracing and the measured SNR actually correlates quite well. This is ray tracing, and this is what we actually measured at each of the clients. And this entire graph is for one such client over various positions of the drone. And this correlation remains consistent across a couple of other clients as well. Of course, we note that there are some variations here which don't really line up exactly as the ray tracing model would show. And that was exactly what we observed as well. So ray tracing actually is able to model shadows quite well, but it cannot model small variations which are caused by various things such as building material, foliage, people walking around, and so on. And because of that, there is an interesting next step required to get the drone to the right position. So even if we place the drone at locations predicted to be really good by ray tracing, we may not get all the gains that we expect. What we did instead is we created a threshold of say 10 percentile top positions where the ray tracing was telling us that gains will be good. But let me clarify one thing. The scale of the ray tracing measurement itself and the measured ones should not be really looked at in this graph. What is more important is the correlation between when it spikes in ray tracing, it also spikes in the measurement. Right, so we look at the top 10% positions predicted by ray tracing and then selected a certain chunk of these which have really robust predictions. So the entire chunk has all points above 10 percentile. With this, we know that there is no roll-off in that chunk within that small region, and so that is probably a region to forward, such that we will not see any lower SNR points in that region. So with these improvements over just having ray tracing, we were able to get SNR gains close to what we would have got if we did a full scan. So to do this first, of course, we have 3 layers of heights, and we actually moved the drone in a raster scan method, and we compared what we can get. This is the oracle. What is the best possible with full scan versus what is possible through DroneNet. Actually selecting a few good locations and then hovering for say 5x5 region. What we also observe is that if you look at particular clients throughput, ray tracing might the gains with respect to placing the drone at positions predicted by our algorithm compared to that of random placement being possibly the median location of median SNR gains, would give us substantial gains for these 3 clients. And DroneNet and what we get when we scan the entire area, that is the oracle, matches quite well. Even here it actually does match quite well. And the gains are about 2x to 3x. 2x to 3x what is possible with just random placement of the drone. Also, for clients which are in more of an open area, the gains are lower, about 40 to 50%, but still this provides us a triage opportunity of not catering to those clients which are probably not going to gain too much. Again, similarly with multiple clients, we see that we get about 40% gains with about 3 to 4 clients put together. And this will again go back to the choosing of the right clients properly. In future work, we would like to concentrate on things that are slightly beyond what we are doing right now. It's not just about placement of drones, but how do we cater to energy? Can we have solar powered drones or gasoline powered drones? What do we do when we have multiple drones together? Also, if we change from being Wi-Fi or cellular to being mmWave, how things change? How do the mappings change? And can we port on readings? Of course, there are other projects which are looking at slightly different but related problems. Both Google's and Facebook's drone and balloon problems are similar. However, they are looking at much longer distance links and are trying to create internet where none exists. Whereas we are looking at much shorter distance links at places where there are shadows. And this problem that we are dealing with will have to be dealt with even with uh, Google balloons and Facebook balloons. In conclusion, we explore if it is possible to use drones and can ra- and we and ray tracing can actually make our life better. All right, thank you, and I will take questions now.